recording. That way I can get it captured. As a reminder, if this class gets at least, what did I say, 29 out of 32 course evaluations, all y'all get 1 point of extra credit. For each of you who submits the Qualtrics survey that you received an email link to last week, each of you gets a point for doing that as well. So up to 2 bonus points, adding to the numerator of your course grade, not the denominator. So those are percentage points, not just points. Because I decided a long time ago that I wasn't going to try to do like extra point math. So each class was worth 100, the end.
I understand.
Yeah, well,
It's easier.
It is easier. So it's more transparent, and then it makes me think about like how to scale things relative to how much time and effort should be involved. But anywho, how is homework 6 going? I asked a few minutes ago. Some folks are done already. Feeling good about that. Some folks have not started. Totally fine.
Not even looked at it.
It's fine. It is. I'm not even mad at that. It's December 10th. It's not due for 9 days, right?
Yeah.
If you have other things that are more pressing, or you just want to put it off, whichever, that's your choice. I will remind folks that we're having office hours next week during the times I would normally be in class, in addition to my other hours, and the TAs are having their hours next week. So ollie oxen free. If you need to get caught up, come on out of hiding, get some help, get the work done. So no questions then? Yes? No? All right. Then let's see. We don't have a formative assessment. The last one of those was already done, so we're getting there. So my plan for today is to try to finish example 5. We have 1 more model to go, and then there's a few slides left in lecture 5. If I don't get through those, I will make a little video to get through those, because I want to spend all of next time on lecture 6, which is called caveats and next steps. All the details that I was sort of glossing over that will come back.
Assumptions made.
Assumptions, yes. I don't like to spend a lot of time talking about assumptions because the answer to what do I do now is not given. Usually in that context, you're just told, well, your residuals are supposed to be normal. They're not. Good luck. And so I'm trying to put together on Thursday the idea of, okay, so if your model has a problem, how do you solve it? And the answer, sadly enough, is going to be take another class in most of these cases and add some other toolkit to your list of abilities. So that's my plan. All right. So we ready to jump back in this?
Yeah.
Ready as we're going to be, at least. Talking about moderation. So just to review where we've been very briefly, we started with a model that has only main effects. And what I mean by that is each predictor has 1 slope and there's no interaction terms. So main effects is a vocabulary term that shows up once you have models with moderators in them, interaction terms and moderation. This is distinguishing just an additive model. So in this case, when we don't have interactions, each of these slopes is unique, marginal, unconditional, meaning like this is the slope of age for everyone, regardless of your standing on the other variables. This is the slope for grip, regardless of your standing, and so on. So each is controlling for the contribution of the other, but they're not conditional on specific values. We then did the model that is for homework 6, in case you haven't started that. It is very parallel in structure to what I'm asking you to do, so this is a template you can follow. We added interactions of gender with age and grip strength to see if those slopes differed between men and women. They did not. So we took those terms out of the model. And the next one then, lots and lots of code for this example. Lots and lots.
And then some.
And some pictures. Yes. And then this is the one we spent most of the time on last time, a quantitative by quantitative interaction. So you do not ever have to cut up continuous predictors to fit interaction terms. I see that still in literature. People do that with the mistaken idea that terms have to be categorical to fit interactions because they learned about interaction terms in the context of ANOVA, in which all the predictors are categorical. You don't have to do it that way. Any predictor can have an interaction term added for it to the model. Doesn't matter what kind. Now, it is true that this is linear only. So like in this model right here, age has a linear slope. grip has a linear slope. That means to create their moderation term, it's the two linear, essentially this is a linear slope moderating the linear slopes. There are other kinds of patterns of moderation. So you could make a quadratic pattern, for instance, if you wanted to. It gets higher orders of complexity, but this is just straight linear by linear. So we looked at this one. Let's do just a little bit of this for practice sake, I think. Let's go to R for this one. Here we go. So in this model output right here, my intercept is cognition. As expected 4. We'll go down the list. What's it all conditional on?
Age 85.
85, grip 9. This is MW, meaning men are the 0, women are the 1. So it would be for men. Likewise, NF is none versus future and none versus current, where none is the 0. So it would be someone without dementia. And now you see why I label my predictors with the centering constant, so that I can look at the output and know exactly what everything means.
Much easier to interpret.
It is. What I often see people do instead is something like this, like they'll put like an underscore C for centered, which just means 0 something else, and now I got to go look at my code earlier to figure out what C means. So I just take the extra step of adding the constants or adding some kind of label that tells me who the 0s and 1s are. And
Do you often write out the full word or not too often? Like, for example, you abbreviate here M and W. Obviously, it's much shorter than writing out men and women, but
I abbreviate to as much as I can before it becomes too difficult to understand.
Okay.
Another thing that I tend to do is name all of my variables with the same number of characters. Keep them, because then my code stays aligned when I'm doing things like in rows.
Cool.
So that's just me being, you know,
But
a little extra with respect to that. But yes, that's my pattern. And I like to use title case to make things a little bit easier to read too. But it's just, you just have to be internally consistent in how you do things. That's the key thing. And in R, if I mistype this, by the way, if I tell it to put this variable in the model, what will happen instead?
Error, or if you have it, then it'll be a weird answer, a different answer.
So if this is somewhere else in your data set, it will use that version instead. If this is not in your data set, you will get an error message. So case sensitive in R and in Stata. For that reason, Stata commands are all in lowercase. If you save a data set in Stata format, it will actually change all your variable names to entirely lowercase for that reason. Don't like it, but it does it by default. So, a little bit of troubleshooting. So, age and grip then. Are these marginal slopes or conditional in this model? Condition, yeah, because they are part of an interaction, that makes them conditional. So this is the age slope when the moderator is 0. So this is the age slope specifically for grip 9. Likewise, this is the grip slope when the moderator is 0. So this is specific to age 85. What about these three? Marginal or conditional?
Seems marginal.
Marginal, they're not part of the interaction terms in this model. So this is the gender difference for everybody. These are the dementia group differences for everybody. That's the idea. All right, 4 kinds of interactions we had, starting with more positive, less positive, more negative, or less negative, boiled down to 2 kinds. Is it making it more or less? And you can add whatever fancy vocabulary words you'd like to put on that. So age has a negative slope in people with average levels of grip strength. The interaction term is positive. So what is it doing to the age slope in people with stronger grip? Y'all take gestures.
Less negative.
Yeah, less negative. So is it making the age slope weaker or stronger? Weaker. It's making the age slope go closer to 0. So less negative, and if you follow it far enough, it would eventually turn positive. If I go the other way, if I talk about the grip strength slope as the thing I care about, what happens to it in older people? Yeah, more positive. So stronger or weaker?
Stronger.
Stronger, yes. So if we put it this way, for every additional year of age, the grip strength slope becomes more positive by 0.12. If I go the other way, the age slope becomes less negative by 0.12 per pound of grip strength. So watch your drop-down menus in homework 6. I'm looking for this. If you're talking about the slope, then you talk about how as the moderator increases, this happens to the slope. It's easy to get this backwards and think about how the age effect depends on age. That would be a quadratic slope instead, age interacting with itself. And what is weird about these kinds of interactions is like these are very specific, right? This is at grip strength 9, this is at age 85, and you might want to know like, well, what would it be at other levels? You could ask for predictions at other levels, or you could request regions of significance, the points at which these things turn on or off. So we talked about that last time. That's sort of an advanced topic, but one that I think is kind of under the radar. So I added an article to your reading list about that. Hopefully that will be useful to you in the future. All right. How are we doing so far? Thumbs up? End of semester thumb check. I think if you still have 2 thumbs at this point, you're doing good. Like that should be the standard right now. Just I have my thumbs and I know where they are. All right. Are you ready for the last model?
Yes.
Okay. Here we go. Page 12. None of what follows is needed for homework 6. So this is just gravy or icing, or pick your metaphor. But I do want you to know how to do qualitative by qualitative, as some call it, or categorical by categorical interactions. So I am leaving in age by grip strength since that was significant. I am now adding sex by dementia. So how many slopes does it take to differentiate my 3 dementia groups? Do we remember? If I have 3 groups, I need 2 slopes. If I have 4 groups, how many do I need? I got 1 answer. If I have 4 groups, how many slopes do I need to differentiate them?
Yeah.
I need 4 fixed effects, but only 3 slopes, because the intercept will be for one of the groups, and then the slopes gets me to each of the others usually. So in this case, I have 3 dementia groups. That means I need 2 slopes. Because I need 2 slopes for the main effect, how many slopes do I need for the interactions involving dementia group? 2 for each. Yep. So I have dementia by gender as an idea. It takes 2 slopes to represent that idea. What if I wanted to do dementia by age? Could I do that?
Mm-hmm.
Sure I could. How many slopes would I need to do dementia by age? Yeah. Still 2, the dementia part.
Why 2 then?
Because I would essentially have age where gender is in each of these.
Yeah.
Yep. So to fully delineate the effect of a variable differing as a function of dementia group, it takes two slopes for each one. Yep. So when I learned interactions involving categorical predictors a very long time ago, this was covered in some of my undergraduate coursework in psychology actually, under analysis of variance, I did not learn the linear model representation of this at all. What I learned was what I call boxes. Erica's laughing. Did you learn boxes too? Are we still doing boxes in undergrad, ONOVA? Excellent. Sam, boxes or linear models? Boxes. Okay. So this is a great place to start, but that's kind of limited because then you're sort of hemmed into one way of thinking about things as opposed to a more general modeling context. So I want to give you both. So the idea of the boxes here, I have asked for these means as part of my output, so that's where they came from. I'll show you that in a second. These are what are known as adjusted means because they are specific to constant values of the other predictors that are in the model. So you have to tell folks what you're holding constant and at what. And so I chose to hold age at 85 and grip at 9, and then I asked for the predicted means for each of these combinations. So these are not going to match the means in the data. They're adjusted. So then I end up with 3 dementia groups. two genders in this example. And then these in here are what are known as cell means, because they are for the unique combination of two different variables. In this example, could be more than that if you want. In contrast, we have what's out here, which are known as marginal means. So these ones and these ones. So 27.63 is the mean of these two numbers equally weighting them. Likewise, this 23 down here is the mean of these three numbers equally weighting them. So equally weighted is an important thing to think about. In this data set, there are far fewer people that currently have dementia than the other groups. So we're essentially upweighting them by giving them the same contribution to the overall mean as the larger groups do. That's a choice that you would have to make in terms of how you want to think about your models, whether you want to do that or not. There's pros and cons to doing it either way. Not weighting it represents your sample more faithfully, but weighting it then, I think, provides each group like an opportunity to contribute to the same extent. So it's a choice, but the most common thing to do is what the Stata option is called as balanced, meaning that you're pretending that these groups are of the same size.
So you would have to state how you were calculating your marginal means if you were reporting this out.
Yes. And the first time that I built this example, I did not get the same numbers out of Stata as I did SAS. And I was like, why
Interesting.
not? They default to different things.
Okay.
Yeah, so Stata defaults to unweighted, I believe, and you have to add the keyword as balanced to get the weighted version. All the things you learn when you try to make results agree across programs. It's
Good and bad.
It is surprisingly challenging for certain things, I will tell you that. So the marginal versus conditional thing here kind of also shows up. So like this is a conditional mean specifically for men who are in the none group, for instance. The marginal mean is for the none group averaging across the two. So this is where the term like marginal mean effect comes from. In this framework, you will get an F-test as to whether these three numbers are different. You'll get one for these two numbers, and then you'll get an interaction term that says, somewhere in here there's some differences, good luck. So we have to learn how to ask for what we want to know. I would argue, though, that the hypothesis test for these three numbers is basically useless. Because this is the mean, not for men or for women, but for someone in the middle, which is a group we have not observed within this sampling design. Likewise, 23 does not characterize all men. It's much closer to the future group, but we're leaving out these ones and these ones. So I don't like these tests. I don't find them useful. So I focus my attention in the cell means. The linear model is representation of this. So based on my coding scheme, let me bold the reference groups here. So beta 0 would give me that cell mean, right here. The first slope then that would be relevant, that's beta 3. That is the main effective gender, conditional on the moderator of dementia group being 0. So then that main effect is going to give me the difference between those two numbers specifically. The main effective gender is conditional on the moderator being 0, which is for the none group. So beta 3 is going to give me this difference. Next ones, beta 4 and beta 5. They are also conditional on the moderator being 0, which is gender. So now beta 4 is going to get me from here to here. That's the difference between these two numbers, because men are the 0. So N versus F for dementia is going to give me these two numbers being different. N versus C is going to compare this one and that one. And then we get into the interaction terms. I will tell you the general rule and then we'll watch it happen in math. An interaction term is a difference of a difference. An interaction term in these designs is a difference of a difference. So for instance, the first one I have here is going to be beta 7. That is going to tell me how this gender difference differs from this gender difference.
Got it.
So I have a gap of about 3 here. I'm just doing the integers, all right? I can't do math on decimals in front of people. It's not going to go well. So I have a gap of about 3 here. I have a gap of about 3 here.
It'll be about 0.
So the interaction term should be pretty close to 0. The differences aren't different. If I have this gender difference and that gender difference, now I have a difference of about 3 and a difference of 11-ish. So the 3 differs from the 11. That's your interaction term. Does that help?
No,
Maybe?
no. I'm
We're
just doing math.
Doing math, yep. Yeah, we'll see the numbers play out.
That's just me just
I'm just
having
trying to
fun
get
with
you
math.
like through the table here. And then there is one more that we might want to know about. This one
No, 2.
and that one.
Mhm.
Do you think we can know that? Or is it going to remain a secret?
You don't know that.
We can know that, right? Well, if I know this one versus that one, and I know this one versus that one, then the missing one is a linear combination. It's a difference in interaction slopes. Yep, so we can get there. So I think the reason why I was not taught the linear model's representation is because it overly complicates these sorts of things. But understanding how it works is really essential in designs in which you don't have all these cells. What if you had no women who currently have dementia? What if that's not there? Well, then you can't specify this interaction term in the usual way. We'll have to figure out what to do with 5 cells instead of 6. That's the end of the lecture 5 here. So foreshadowing that. Okay, so the questions we're answering then. Does the effect of sex on cognition vary by dementia group? Or does the effect of dementia on cognition vary by sex? The interaction terms are going to work the same way. So to implement this, in Stata we have our friend the hashtag or #, take your pick. Note that I have created all of the binary contrasts myself, and so everything in here is a C dot variable, meaning treated as continuous. There is an alternative that I have deliberately hidden from you. It's I dot instead, and what that does is make the dummy codes for you and put them in the model. That one is easier to screw up if you're new to the game. And it makes the code more inconsistent across packages. This version corresponds directly to the linear model representation of this analysis, so I like it for transparency's sake. But that isn't the only game in town. All right, here's my model. Is this a good model? What do we think? What do I look at?
Significant value.
Yeah, the model's significant. What's that mean?
It reasonably predicts.
Yeah, the 8 slopes aren't 0. That's one way to think about it. P-values are probabilities, right? This is the probability of getting slopes that are this big, all 8 of them, if in reality they're actually 0. Very unlikely.
Keep that phrase in mind while you're doing your homework.
Yes. Cough, cough, homework question. P-values are the probability of getting a result that big or bigger if the true result is the null hypothesis, which is usually 0. Yes, indeed. So, we know that the 8 slopes aren't 0. How good of a job did they do in predicting this outcome? We have significantly good so far. What do I need to think about? Yeah. This model has explained about 30% of the variance in cognition. That ain't bad. It's fake data, but it's not bad. Another way to think about it is if I take the square root of 0.3, that's the correlation. That's the correlation between the y hat that's predicted by the model and the real one. So another way of saying this is that the predicted cognition is significantly correlated with the real one, p less than 0.05 or 0.0 anything. I want to do the R output for the model because I like the way it's rearranged better. I do, because constant should be first.
So R has a purpose.
There we go. Okay. Are any of my slopes still marginal at this point?
Well, of the ones highlighted.
Of the ones highlighted, are any of these slopes still marginal at this point? What do we think? Got 1 vote for no, 2 votes for no. I would agree. All of these variables are now part of interaction terms. So they're conditional on something. Conditional on what, though, depends on which particular interactions they're in. So age and grip are conditional on each other because they interact. However, age and grip are not conditional on gender or dementia because they don't interact. Likewise, gender and dementia are conditional on each other because they interact, but their slopes are not conditional on age or grip because they don't have that interaction term. So the rules are straightforward. If it's in an interaction, its slope is conditional on what it interacts with. But keeping track of all those individual results can be a little bit tricky. Okay. So this is my gender difference. Let me make the numbers bigger here. It's a negative number. Who's higher? The 0 group or the 1 group? Who's higher? Yeah, the zeros are, because the coefficient applies to the 1. So minus 2.9 is how the 1 group differs from the 0 group, how the women differ from the men. And I have to say it that way to get the direction correct.
If you hold them constant at 85 and 9, correct? Or no, because they aren't interacting.
Yeah,
Fine.
not, so this is not constant at 85 and 9 because gender doesn't interact with
they
these
are
in this model. It did in like 2 models ago,
Yes,
but not this one, yep.
okay.
But this is specific to what, though? The gender difference is minus 2.9 in what dementia group? When do these terms go away? Your choices are N, F, or C. N is 0.
N is 0.
N is 0. Zoomers, I'm watching the chat. You can play along too. Question is, this is the dementia group difference, or excuse me, gender group difference, conditional on dementia. Which one? The N group is where the 0 group for both of these. So this will be the difference between men and women who don't have dementia. In those people, is the difference significant? Yes, it is. Here's my p-value column. Okay. What happens to that gender difference in folks who are eventually going to get dementia? Future is 1. Your choices are more something or less something. And it's less something because they're opposite in sign. If they're the same sign, it's more. It's that straightforward. I know, it's beautiful. So in the future group, the gender difference is reduced. So this is the first interaction that we looked at in the table of cell means, how this was 3-ish and that was 3-ish. So to get to the second one, I would take this gender slope and add to it 1 times the interaction term to turn it on for future. And so that gets us pretty close to 3 still.
Mhm.
Now that one is probably not significant. No, it is not.
It's terrible.
What that means is that the extent to which men outperform women is equivalent in people who do not have dementia and people who are eventually going to have it. The gender gap is the same. A lack of a difference of a difference. Now, what about people who are already having dementia? Is the gender gap more or less in people who already have it, as indicated by DEM-NC of 1? I got a negative 2.9 and a negative 7.9.
Is it gonna be more?
Yeah, because they're the same sign.
Yeah.
So yeah, the gender gap is larger, is stronger in people who already have dementia. So in the table, we had a 3-ish difference, and then we had an 11-ish difference.
Mhm.
And the difference between 3-ish and 11-ish is right here.
Mhm.
An interaction term is a difference of a difference. Now, what about future versus current?
Less.
Yeah, I need these two. So I can take minus 0.7 and subtract this from it, and then I get what it is. So slightly less, yep. Let's go the other way. People who are eventually going to get dementia are lower in cognition than people who are not, by 6. End of the sentence or more needed?
More because of condition?
Yeah, who is this the dementia group difference for, men or women? It's for men because they're the 0 group in this coding scheme. You have to know who your zeros are. So then what happens in women? Is the dementia effect bigger or smaller?
Smaller.
Smaller, opposite in sign. Yep. It's negative and it becomes less negative in women. What about this dementia group difference? 12. Those are the difference between people who already have it are 12 lower than the people who never are going to have it. What happens to that difference in women?
Gets worse.
Much worse. So in terms of our, let's see if I can get the results for the table. I have a table in here that I wanted to see. Do I have it in here? I may have it and it's just zoomed out too far for me to see it. That happens. I have it. Where is it? Where is it? Where is it? I know what I'm looking for. Maybe it's only in my brain though. Yeah, I must not have put it in here. I have another version of this handout that has a table in it. I swear I'm not hallucinating. But when we're talking about doing the dementia group differences, we're going this way. So for instance, what we just looked at is none versus current. So that difference is like 12-ish. And this difference is like 20-ish.
Mm-hmm.
And so 12 versus 20, that difference of differences is 8. That's your interaction term. So there's one more then that we don't know about, and that's the linear combination of future versus current. Right, there we go. So that would be the same way here. Now, is there an interaction of gender by dementia? Yes or no question?
Depends on which one, if you're looking at versus
Depends on which
future.
one you're looking at, but they work together though.
Mm-hmm.
Like I can't just like look at one because they all fit as part of a puzzle. So if I want to find out whether the two interaction terms together contribute significantly to the model, what do I need to do?
You have down the one.
You gotta ask for it.
Mm-hmm.
So each of these p-values can be used to test the one thing that the p-value refers to. But if we want to talk about the contribution of gender by dementia as a set of slopes, I need both of them. Yep. So essentially what I need to do is compare back to the model that didn't have them, see what that R-square was, see how much I've gained, and I can do an F-test for that gain. So now my R-square is up to 0.2984. That is a net change of about 1%. Woohoo! Degrees of freedom is 2. Why?
Because I got two slopes.
2 slopes. Yep. And I could put in 541 more if I wanted to. But we're not going to do that. F of 3.5, p-value of 0.03. So they significantly improved the R-square, and this is by how much? Now there's other things that I could ask for as well, same premise. Is there an effective dementia, say, in men? That's a 2-slope question, because dementia has 3 groups. So I could lump these 2 slopes together to get a hypothesis test for that combination, and that's what I did here. So I don't think you've seen one of these yet. This is a combination of 2 different types of approaches to identifying things. So within the parentheses, this is the first dementia slope main effect. The one over here is for the other one. By separating these with a comma and writing them as 2 separate things, what I'm asking it to do is to provide a joint test of both of them. I'm not adding them together. To get what it is for women, though, I go back up here. These are specific to men, right? Because they're the 0. Are these the dementia effects for women? Because that is the most common way people misinterpret this. They say, oh, these are the ones for women.
It's for men.
Yeah, these are for men. Yeah, stop it. These are for men. And these are differences of differences. So these down here are not what they are for women. They're how different the women's slopes are relative to the men's. So if I want to find out what the dementia effect is for women for none versus future, I have to add this one and that one together. And that gets me to the difference for women. Likewise, if I want to know what this is for women, I got to add those 2 together. So to answer this question, is there a main effect of dementia in women? I got to add and lump at the same time. That's technical language, I know. I'm adding the main effect and the interaction to get a different conditional effect for women, but I need to do that twice, one for each of the contrasts. That's the lumping part. So the code down here does that within a set. So this is adding the main effect and the interaction for N versus F. This is adding the main effect and the interaction for N versus C. And then the lumping is happening by separating these with a comma. Then we get some pictures. So I'm using prediction, which is an a function within R package, I think, that has the same name so that I can ask for predicted outcomes. So how many predicted outcomes am I going to get from this code here? I'm holding age and grip constant at 0, and then I'm varying dementia from 0 to 1, sex from 0 to 1, and the other dementia from 0 to 1 as well. How many combinations is this going to yield? And feel free to read the screen below you too. It's fine.
2 to the 3rd.
2 to the 3rd.
Sorry.
Yes, otherwise known as 8. 2 by 2 by 2. How many cells do I have in my design? Do I have 8 cells?
Yes.
I had 2 dementia groups, or 3 dementia groups, excuse me, in the rows by 2 genders. So I actually have 6 combinations. So if I just use this code, it's going to not understand that 2 of these are logical impossibilities. That would be when both dementia contrasts are 1 at the same time. There's nobody like that in the data set. And R don't care. All right, it's like, here you go, here's your prediction.
It makes numbers however you want.
Exactly. So it's up to us to make sure that the numbers make sense. So the code down here that I use to make the pictures is essentially taking these lines and removing them. I'm saying make a new variable that's the sum of these two. If the row has a sum that is less than 2, then keep it. So I'm essentially just manually writing code to remove those 2 lines. So then we got what's left. Then, because I need it to understand that I have a 3-group problem, I'm recreating the original 3-group variable out of the 0s and 1s so I can make a picture out of it. And here's my pictures. Now, I know lines aren't the best for these things, but if you can work with me on this. So I have a 1 and a 2 and a 3. And I have different lines for men and for women. So here's the gender difference in group 1. Here's the gender difference in group 2, and here's the gender difference in group 3. There's a bigger difference if you already have dementia than if you don't ever or you don't have it yet. That's one way to talk about it. The other is to say dementia is bad for you, right? These are broken looking slopes because I have one slope that goes from 1 to 2 and then another one that would get me from 2 to 3. But dementia is more bad for you if you're a woman, changing from 2 to 3. So like this part from 1 to 2 looks pretty much the same, and the hypothesis test supported that. There is a gap of about 3 here and about 3 here, and the effect of dementia is pretty much the same as well, about 6. From here, though, this is where the interaction is happening. It's the future versus current. So that is yet another reason why we can't just look at these 2 interactions that are given by the model, because there's only 2 of the 3 that we would potentially want to look at. And it gets exponentially more complicated when you have more groups. What you're provided with is only a small part of what's possible. So the omnibus tests are meant to protect against that. So I made 2 different pictures from 2 different perspectives. This one is emphasizing the gender effect as the slope, and then these are for the different groups. So there's a bigger gender effect in the current group than in the others. So the same logic of how you would get simple slopes. If I want to know the gender slope, for instance, grab all the terms that have it, factor out gender, and that's what's left. So I need to fill in 2 different values for the moderator for each spot to be able to find those. For the dementia slopes, only 1 moderator for those, so that simplifies a little bit. Down here, and I did the same thing in the Stata output, or the Stata code, I am writing the interactions from 2 different perspectives to get you to recognize that it is the same thing. So the first interaction term, which was the 0.16, so not much of a difference between 2 differences, I can either talk about that as how the sex effect differs between the none and future groups, or I can talk about it as how the difference between none and future differs between men and women. Either of those is correct, and it's the same number either way. Likewise, the next contrast is between none and current. I can talk about how the sex difference varies across those groups, or how the group difference varies between men and women. The third one is the missing contrast that I have to ask for. And that is the difference of future versus current, because that is the non-reference group. And if you look at my code here, you see -1 and 1. Now, where did that come from? Here's the logic. If I take 0 and subtract 1, what do I get? Yeah, -1. Because this is how none and future differ, this is how none and current differ. If I want the difference of the differences, I'm literally subtracting the 0s and 1s you came up with. So 0 minus 1 is why this is -1. 1 minus 0 is 1. So this works out to be beta 8 minus beta 7, the missing interaction contrast. And here are all the numbers from all the codes put all together here. So then you can talk about all the differences that you might be interested in and whether they're significant, and you can map that onto the pictures as well, if you wanted to. And then effect sizes, regions of significance, and all the good stuff. There, that's technical language. And because I'm nice, words.
Most important part. Well,
Words.
I shouldn't say the most, but a
No,
very,
it is
but,
the
but
most
it is a
important.
very important part.
Yeah, because being able to put your results into words is how you disseminate your findings to the field, and that's, quite frankly, the currency by which you will get jobs, publications. So knowing how to explain this stuff is helpful. This is probably overkill to what a results section would be. It has a lot more detail to it, but I wanted it to be explanatory to you as opposed to just demonstrative in terms of reporting. So, in particular, the model implied terms. I'm telling how they were computed out of the model coefficients. I wouldn't normally bother to do that. In the table, though, that I built, I did do that. So I have a model equation, which means I can label the terms that go with the equation, and then I can describe all the differences. So for instance, the main effect of sex in the model is specifically for the none group. That's given directly by beta 3. But I can report the results for the other groups as found through these linear combinations in the same spot. So everything can be in one table, even if you had to run different commands to get all the pieces. I think that's less confusing. And then D and R effect sizes as well for that. There. Ta-da! So I know that was a lot, but I just wanted to give you an example of what a two interaction slope model would look like. So you'll see more of those in the future. Questions on any of that? All right, let me go back up to, oh, no, too far. I know where I want to go. Let me go back to the slides. Categorical predictors with issues. Based on a true story. This is slide 26, so just a few more here and then we'll see how much I might need to do outside of class. So experimental designs in which you have fully crossed conditions, like I just showed you, there's somebody in every group, are desirable, but not always possible. So I want to describe two situations in which you would need to do something a little bit different to get at the idea of an interaction. The first I call ANOVA with a hole in it. And the other is when predictors logically don't apply to everyone in your sample. And the solution to both of these is something called nested effects. And they look like interaction terms, but they're not. They work differently. So I want to talk a little bit about those in case you're in this situation. So here's a traditional way of looking at analysis of variance, interaction terms among categorical predictors. So this is just like the table I showed you. Let's say that we have a dimension of A versus B, another dimension of 1, 2, and 3, and I've got 6 possible combinations here. So I would get a marginal f-test about whether A and B differ on the whole, whether 1, 2, and 3 differ on the whole, and then an interaction term, whether there's some kind of difference in here. And there's 2 degrees of freedom that it takes to fill out this whole table. But I would argue these are not helpful because they're averaging over the other thing that we care about. So I would rather focus on decomposing the interaction with the terms in the table. Cool. So then this is the breakdown. This is what we tried to do for the example. Here's the math behind it. So if I have beta 0, that's my intercept. Beta 1 gives me this difference between these two because that's where the interacting variable would be 0. Beta 2 and 3 go this way because this would be my reference category. And then the interactions give me the differences of the differences. So that's the green things here are meant to be like how much A1 differs from A2, that's one difference. How much B1 differs from B2, that's another difference. The green interaction term is the difference of those differences. And it goes the other way too. The same green term is also going to tell me how the difference between A1 and B1 differs from the difference between A2 and B2. It works both ways. It's magic.
Same answers.
It is. It is, because interactions are interpreted either way. Yep. So then you can figure out what any of these other differences would be because you have the ingredients, you have the slopes, and you can lump them together and test things. And every software package that people would use nowadays has this capability. But if you don't have all the combinations, you can't do it this way. You have to do something else. So here's a real world example. I once had a student come to me and ask the question, what if your ANOVA has a hole in it? And I was like, tell me more. Well, it turned out that they were doing this experimental design, taking kids and trying to make them better at math. Great. So then they have 1 year, they're calling cohort 1, where they randomly assign kids to control and treatment, make them better at math. Great. They do it again the next time, and then the grant ran out of money. And they didn't have enough funds for a control group in cohort 3, but they had a treatment group. So there's no way that I could fit this into a standard main effect interaction situation because my ANOVA has a hole in it. But I can still work with it though by creating nested effects. So I'm going to start by making beta 0 this cell right here. That's going to be my reference coding. That's my choice. That's what I'm going to start with. So cohort 3 is going to be the reference specifically for treatment. Now if I want to talk about treatment 3 versus 1, or excuse me, time 3 versus, what am I doing here? Yeah. Okay, I got it. Time 3. Cohorts here. So if I have this versus this, and I have this versus this, I can do that. But I can't talk about this way unless I set it up with nested effects. So I can say T1 times treatment versus control. That means cohort 1. T1 doesn't have a main effect. Likewise, T2 doesn't have a main effect. So that limits them to just focusing on these cells. It's like a filter, essentially. Like it's only turning on the effect for the kinds that it's available. And it still works out that I have 5 fixed effects for 5 means. I just have to drop one of the main effects to make this whole situation work. So you can do this when you have these types of designs. Here's another example. So again, in the context of older adults and dementia. Let's say that I have a study examining changes over time in cognitive-related outcomes, and not everybody in my sample has dementia. Well, can I put in how long they've had dementia as a predictor? If you don't have it, that's a stupid question. Like, if something is a logical impossibility, can you still include it as a predictor? Yes, you can, but as a nested effect. So let's say that I have 3 different groups here. I have people with no dementia in my sample. I have people with Alzheimer's type and people with vascular, which is 2 specific kinds. So I'm going to create one binary variable that differentiates yes or no having dementia. And I'm calling this dem yes because that's when it's on, a 1. Okay. Then I'm going to compute another binary variable. It's not technically binary in this case, it's just dichotomous. That is whether it's Alzheimer's or vascular. And note the coding scheme on this, minus 0.5 and plus 0.5. You have not seen this yet this semester.
Actually, you did.
I showed it to you,
showed
I
it
think,
a
after class.
long time ago.
Not in an example, though.
Right.
Here's my rationale. I have 3 groups, but I might want to be able to collapse across the 2 kinds if they're the same. So if these average out to 0, then I can talk about yes versus no exclusively. If I want to include it, then I can further differentiate A versus V, but I don't have to have none versus AD and none versus VA. So I can optionally include this second column if I want to, but I don't have to. This gives me the capacity to split these 2 apart if I want to. Now, when I've seen this in textbooks and in the literature, I more often see plus or minus 1 for these 2 cells. Any guesses as to why I did plus or minus 0.5 instead?
Because you used 1 in the first column?
I use 0s and 1s here in a traditional binary variable, but that's
Yes.
not why, but it's related.
Okay.
How far apart are -1 and 1?
2.
It's a change of 2, right? What's the definition of a slope? The change in y for a 1 unit change in x, not 2. So if I coded this plus or minus 1, I would have to take that slope and cut it in half to interpret it.
Mm-hmm.
It's a 2 unit change. I don't want to do that. That's annoying. So I created a 1 unit change by changing the scale. Now dementia, how long have you had it? For people who don't have it, I'm going to put zeros in, but they're not real zeros. They're just like not applicable, essentially. So for everybody who is applicable, I'm going to center it, say 5 years is near the mean. Let's do that. So then I would create this column with the actual numbers for them. So here's the trick. I'm not going to put in a main effect of dementia time because it doesn't apply to everybody. It only applies to these two groups. So I'm going to put in a main effect only for these two groups. Here's how it would look. So I have an intercept. Given my coding scheme, that would be somebody who has no dementia. Okay. Then I have one slope for the difference between the no and the yes groups. So this is the effect of having dementia in people who've had it for 5 years, given the rest of the model. A versus V here, that is splitting apart the two kinds. So that's the mean difference between those two groups. And then note dementia time minus 5 is not in as a main effect. It's only in as what looks like an interaction term. Right? These two variables are multiplied together. We would normally think that's an interaction term. It's not interpreted that way in this case. Think of dem yes as a light switch. When it's on, when it's 1, time will contribute to the prediction. When it's off, when it's dementia no, this whole thing cancels away.
Oh, okay.
And the same thing happens over here. So you are turning on the effects of how long you've had dementia within the groups that are coded 1 for dementia yes, and then further differentiating them between the kinds here. So it is okay to include predictors that are logically not relevant to some people if you do it as a nested effect in this capability. So that is one thing that you can do. So when would you want to do this? A few other examples. What I call if and how much semi-continuous predictors. So let's say that you have something like degree of severity of childhood abuse. You have a scale. You ask them a bunch of questions about people being mean to you, you tally them up, and you have some sort of severity. In most samples, I would hope, there will be a selection of folks who have zeros, right? They were never abused. Nothing bad happened to them. And then unfortunately, there will be people who have some value. Now, if I think about like qualitatively, is the difference between moving from no bad things to 1 bad thing likely to be the same as like 27 bad things to 28? Like that initial switch off of 0 is a big deal. Like you are abused or not if you've moved off 0. So we can set up predictors that work that way. So I could take one binary variable and say, no if you have a 0, 1 if you have anything else. And that is essentially abused or not. And then within the people who were abused, I could say how bad was it. And I can multiply that binary variable, like if you're a 1 for having anything, then I want a slope to contribute to your score for your level of severity. So then you don't have to have it be truly categorical or truly continuous. It can be semi-continuous. So I think of those as if and how much. In my textbook, if you would stick around for the longitudinal class at some point, you will get to see this example. I took data from my master's thesis in which I had groups of young adults and older adults. The younger adults were all psychology introductory freshmen who varied in age from like 17 to 19 for the most part, and the older adults varied from 60 to 85, so like a much wider range. So in that setup, what I did is create a dummy code for are you in the older group, 1, if not you're a 0, and then what is the effective age in the older group? So then I could look at whether being 60 versus 65 versus 70 matters only in that group. So a semi-continuous approach. So I did the severity one. Yeah. Incomplete data can sort of be handled this way. So if you have choices for are you young, old, or prefer not to answer? Right? Prefer not to answer could be considered missing data, or they could just not write something down and that shows they preferred not to answer. Do you think it's random, though, that someone would pick that? Probably not. So you could include didn't answer as a category. Like that could be part of your model. People who didn't answer turn out to have higher outcomes than people who did answer. That's harder to do for continuous variables, but for categorical, it certainly would work that well. But you could have a slope in the group that has information in that case. So another use of this that you will see if you come back next semester is in multivariate models, where you're predicting more than one outcome at the same time. The easiest way to set those up is a series of nested effects as well. So just some extra stuff to talk about, and now I don't have to make a separate video. Yay! You know how proud of myself I am when my class material actually fits into the space I have allowed for it? It never happens. It's happening this week. So I know this is kind of a lot. I just, again, wanted to provide you with some breadcrumbs for your future selves if you're dealing with sort of weird situations in which your predictors don't all apply to everyone in your sample. Question?
Can you have more than one hole in your table, and would you treat it the same way?
Yes. You can have more than one hole, but you'd have to set things up so that you're never referencing that hole as part of something.
Okay.
Yep. Other questions or things you want to chat about before we adjourn for the week? Not the week, just the day. It's garbage day. Getting ahead of myself. All right, then how about we call it early? 10 minutes of your life back? Sound good?
Woo.
All right, yes, so class Thursday, our last time together. Let us know if you need anything before then. Hope to see you all there. And you can be working on homework 6. Bye for now. Bye, Zoomers. Bye, Roomers.